So, and that's also totally normal, because if I'm just giving a lecture, I could cover the material. If I wasn't stopping to do the practice problems and stuff like that, I can do the material in an hour. So we might finish a little early. We'll see how it goes. Yeah, how do they look?
It's all yellow.
Nice.
Their products look a little bit more pure than mine. At least we haven't purified them yet. So
Yeah, when we do a recrystallization, that helps a lot. Like, we'll take a little bit of the crude to do a melting point, and then we'll recrystallize it and filter it and do it again. And we should see good product. I'm pretty optimistic. It looked like there was a lot of it.
Probably like 10% of what was in the vial, but it was
I mean, it was like
round bottom that was full.
Yeah. And we put in like 3.5 grams of the benzophenone, right? That's a lot.
That is a lot.
So if we wind up with 0.5 gram of product, that's actually not half bad, considering we made the Greenyard reagent a week before we used it, called an audible, and are kind of going from there. So
yeah, that's why.
exactly. Awesome. So we're going to jump into carbonyls today. So the reactions that we did the other day, the nucleophilic substitution aromatic and elimination addition are the last two mechanisms of the aromatic section. So we'll move on to carbonyls, and that's really where we're going to spend probably the bulk of our time for the rest of this class is in, hey Jerry, is in various types of carbonyls. We'll spend a little bit of time on aldehydes and ketones. It turns out they actually aren't that interesting in terms of reactions themselves, but it turns out the alpha carbons of aldehydes and ketones are actually reactive as well, because of the resonance that you get from having that carbonyl group. So there's a whole chapter on alpha carbon chemistry, and then we'll get into the acid derivatives probably after midterm. The aldehydes, ketones, and then alpha carbon reactions will probably take us to midterms.
When's the midterm expected?
So this is the end of week 3. I don't remember what I have on it'll either be week 6 or week 7.
Okay.
Based on how fast we're going through the material, I'm tending to think week 6. But we'll do the same thing where the last lecture beforehand is review. So we'll take a whole week just to do the midterm between the review and then taking the test. Which again, so if we spend a week on aldehydes and ketones and a week on alpha carbons, that brings us through week 5, or like halfway through week 5, and then that sets us up to do week 6 test. I'm going to go back and double check on the syllabus since you're asking, just to make sure. There's obviously we can be flexible with only 3 students in here. We'll do what works for us.
Yeah, I was just trying to play through the physics and calculus. They're trying to put it on the same day, and they sort of.
So yeah, when that gets settled, when physics and calculus figure out where they're going to do their tests, let me know, and we'll make sure our test is not the same.
Yeah, we this Friday.
Okay, cool.
The other classes, I don't have midterms or anything like that, so you can be the deciding factor for when.
Okay, right. Maybe postpone hers and then have the physics and calculus together, and then I taught Kathy and postpone hers to go. It's got a little bit more time on both.
Cool. Also, I like to throw this as an example. This is something that somebody submitted on one of their quizzes. And you know, it's actually as messy as it looks, it's actually a pretty good way of explaining what's going on, but it can be a little neater, because when you start turning in homework assignments that look like this, you start looking like Charlie Kelly. But at the same time, like, yeah, we're all in this together, and I knew more or less what that student was trying to say. So maybe just a finalized, like, here's my actual logic. This was all just me thinking on paper. It can be helpful. But I saved that figure a couple years ago and I'd still reference it because, like, look, this is how you can show your work. This still counts because it's still neat enough for me to read.
It's the perfect picture for a lot of things.
Right, exactly. It did not save. I got rid of that section. All right. Those were just the reactions that we did the other day. So when we're talking about carbonyls, go back to our original definition of carbonyl function groups, or kind of the bottom of them. We have a total of 7 carbonyl-based functional groups, but really they fall into 2 classes. Class 1 carbonyls are carbonyls where you also have a good leaving group attached. It doesn't have to be a great leaving group. For instance, carboxylic acid, we don't usually think of a hydroxide as a good leaving group, but it is a leaving group. So it's a better leaving group than, say, an R group. Your leaving group, in some cases, for an acid anhydride, your leaving group is an entire acid winds up leaving when these things go. Okay, so if this is our carbonyl here, that's a really good leaving group. And in general, the better the leaving group, the more reactive these things are. So there's a leaving group. There's a chloride or a bromide generally. And we have it's called an acyl halide. Typically, it's either a chloride or a bromide. Chloride is more common, actually. Out of those, what would you expect to be the best leaving group? Or sorry, the worst leaving group? So a good leaving group typically means a bad base, and a strong base is a bad leaving group. So what's the strongest base up there? Attached to the carbonyl. Not that one. We know it's not gonna be that one. That's a good leaving group. That's an even stronger, right?
Yeah.
These are going to be roughly the same in terms of their reactivity. Esters and acids really readily get converted back and forth because it's still an oxygen as a leaving group, whether it's an OH minus or if it's a deprotonated alcohol. They're still roughly the same strength as a base, right? Your pKa's for methoxide are about the same as your pKa for hydroxide. So amides wind up being the least reactive or the most stable out of these. But again, we're going to spend a whole chapter on these coming up after the midterm. But the result of that is that class 1 carbonyls really easily go through substitution reactions. It's pretty easy. They don't look like a standard SN1, SN2, but it's not all that different, frankly. On the other hand, our class 2 carbonyls, aldehydes and ketones, our leaving groups are either a hydride or an R group. We know that carbons aren't good leaving groups, and hydrogens are only good leaving groups in the sense of doing a proton transfer. In this case, if it's acting as a leaving group, it's a hydride because it's got to bring the electrons with it. So they're not going to go through substitution reactions very easily. What we see instead is they're much more likely to go through addition reactions. And that's what we did in lab with the Grignard reagent, right? We used a nucleophile and a ketone to do an addition reaction at that carbonyl carbon. And again, it's going to be a slightly different addition mechanism because it's not a symmetrical pi bond. We have a partial positive on the carbon, which actually makes it even a little bit easier to predict what's going to happen, because we know if we're using a nucleophile, we know exactly where that nucleophile is going to attack. your nucleophiles are never going to attack the oxygen there, right? Because the oxygen's got a partial negative. Right, and again, just to recap, big difference between aldehydes and ketones is just that an aldehyde is at the end of a carbon chain and ketones in the middle of a carbon chain. The other way of thinking about it is an aldehyde has one R group attached. The ketone has two R groups attached. With one exception. There's one aldehyde that doesn't have an R group attached. What would it look like?
I was gonna say formic acid, but I know it's not.
Close.
But it is close, yeah.
That's the acid form.
The acid form.
Formaldehyde.
Formaldehyde, yeah.
Or the is the prefix meaning one from before they used IUPAC prefixes.
Oh, okay.
So formate, formic acid,
Yeah,
formaldehyde. And it's interesting, it actually comes from the Greek word for ant. Because the first place they isolated formic acid was from the bodily fluids inside of ants. And so if you've ever had like an ant problem in your kitchen, they had to squish like 5 at once.
Oh, I'm so
There's like a really
sensitive to that smell. Oh god.
that's the smell of formic acid.
Really, is it?
Yeah.
Oh god.
Just formic acid, I guess, I used to eat ants when I was a kid, they're like sour. They're like, no.
Yeah, they are very sour because of the formic acid.
I used to mess up brothers with feed things.
You know, they're a good source of protein. They're really common. It's really interesting. Insects in general are really interesting from a nutritional point of view because they don't have blood. They don't have a circulatory system. So they have other fluids instead to serve other purposes, one of which is formic acid. And lots of cultures, Southeast Asia and Eastern Africa, both use ants as food sources traditionally. Crickets and termites.
You know,
Termites
crickets
are
are a
big in
lot better.
Africa.
So I've had crickets, they're a lot better. But I've never had ants, so I'm just your advanced.
Wait your tongue.
South America, because there's so many ant species that are so active in South America. So formaldehyde actually is just gonna look like this. So technically not an aldehyde. I don't, if we're splitting hairs, I'm not even sure if you would consider that an aldehyde because it doesn't have an R group. Or if it's just its own thing. Probably it's just its own thing. Because it does react, it's super reactive, more reactive than standard aldehydes. Some more examples. So vanillin and benzaldehyde, both simple aldehydes, aromatic aldehydes. Cinnamaldehyde we worked with. There's carbone. We might have been able to use carbone, remember at the end of last quarter when we did that substitution reaction?
We could have.
We probably could, there's still got a little bit of resonance there, but a lot less than the whole benzene ring, so carbone might have worked for that bromination as well.
Was it in the stock room?
Yeah,
Oh.
we don't have a lot of it, because it's mainly like, we take it out. And, hey, check it out, you can smell this, it smells interesting. But we probably could have used that, I'll have to keep that in mind for, although the tetrahydrofuran, whatever we want to use. Sulfine,
Yeah.
that wound up working pretty well. Then steroids, testosterone, progesterone, are the two that were already pulled out in the textbook when I grabbed these, but a lot of hormones. In fact, the suffix on the end of hormone comes from the fact that a big chunk of the classical hormones are ketones. Not all of them, obviously, and And when you get into the biology side of things, the definition of hormone is a little bit different. It's not chemistry based, it's function based in the body. Right, so like the biochem definition of a hormone is a chemical messenger that acts through the bloodstream. So anything that changes the way your body functions from one organ to another that passes that message through the bloodstream is a hormone. And anything that does the same function but through the nervous system is a neurotransmitter.
Yeah.
So there's some hormones that are also neurotransmitters, some neurotransmitters that are also hormones. As well, so then it gets more into the function aspect and less into the structure aspect when it comes to defining some of those. Which I'm trying to think of where I learned this, but that's the difference between anatomy and physiology. Is that one is about the form and one is about the function. I can never remember which is which. I think anatomy is the form and physiology is the function.
Yeah.
So. Which was an interesting distinction. I had never thought about why it's called anatomy and physiology, because I always thought they were synonyms. But turns out slightly. Okay. Yeah. Okay. All right, so naming these. New functional groups, we got new nomenclature. Good news is it's pretty straightforward. If it's an aldehyde, we just drop the E, name it, following our normal naming patterns. Drop the E and add AL. So it's really just like an because alcohol was drop the E and add OL. Aldehydes is drop the E and add AL. One slight caveat is we generally don't need to add a locant. Because whatever an aldehyde by definition will be at the end of a carbon chain. So it will always be on carbon 1. So we don't need to say it's one butanol.
But like a ketone would be, if there's multiple ketones,
Ketone,
then yeah, you can
specify. Exactly. And then just because this would get really weird to name, if we try to name this just using the other nomenclature, it would be like cyclohexyl formaldehyde. But it's not really going to behave like formaldehyde. So we just use that the term carbonyls. Basically name it like it's just the cyclo ring and just stick carbonyls on. And then up here as well, it's in the interest of keeping things short, AL is the easiest way to do it, but that does get hard to pronounce and you really have to be careful to enunciate so that butanol doesn't get confused with butanol. If you're worried about that, you can just say the word aldehyde. Butanaldehyde is just as acceptable as butanol. So if you're saying it verbally, especially, it can be to your advantage to do that. Other than that, it's the same rules as we've been doing, right? Nothing tricky about it. Same thing for ketones. Except instead of putting AL at the end, we put O at the end. So butane becomes butanone. If there's more than one possible place where you can put ketone, we add locant. No surprise there. And either option works. 3-heptanone or heptan-3-one are both perfectly acceptable. The old school way of naming these was basically you named it by just saying 2 alkyl groups attached to a ketone. we call that carbonyl ketone, and you just say. Name the other two like their branches. So ethyl propyl ketone. The one that's really calming, that I've mentioned before, gets used as a paint thinner a lot, is methyl ethyl ketone. And you can still buy methyl ethyl ketone at hardware stores in Nevada. But it also gets shortened a lot of the time to MEK. If you work in mechanic shops or anything like that, you might seen people refer to MEK before, or if you worked with painters before, which stands for methyl ethyl ketone, which we would name as butanone. And then, so technically acetone's the common name. The IUPAC name for acetone would be what? Propanone. Not. That's one of the common names. I think it's almost as ingrained with benzene. I don't think it's going anywhere. But if you go look in the stock room, we probably have a bottle labeled as propanone. It's probably stored with the acetone, depending on where you get it, what you're using it for. It might be, if you're using it as a solvent, it's almost always going to get called acetone. If you're using it as a reactant, then it might get sold as propanone at a higher level of purity. But that depends a lot on just on the vendor. So let's practice. Let's do some nomenclature practice. Yay. Take a couple minutes. I'll give you a head start. There's obviously lots of details now. We've added enough wrinkles to our nomenclature that we can say just follow the same rules. It's nothing too tricky, but it does get fairly complex. I mentioned to Zeke that I did not sleep much last night, so if I missed something, bear with me. My youngest was sick last night, so. And when the baby's sick, nobody sleeps. So our longest continuous carbon chain. Right there. 6. So that's gonna be, and it's an aldehyde, so it's gonna be hexanal. I realized it didn't, I edited my old slides and got rid of the answer. But then it didn't save my edits. So the answer's already there. For the top two.
Oh, it's a problem. Oh.
We can still go through the process though,
Yeah.
so.
Oh, I didn't even.
X amount.
Okay, well,
It blends in, section right above it. And then we've got a dimethyl, both on the same carbon. And again, because the aldehyde is the last thing in our name, it has priority, so it will always be carbon 1. So that makes it 2,2-dimethyl 5,5-dibromo hexanone. So in which case it would be 2,2,5,5 tetramethyl.
Okay, perfect.
Over here, it's still 6 carbons in a row. I guess just a note about skeletal structures. It's not wrong to leave off the hydrogen on an aldehyde. But for whatever reason, by convention, when you're drawing out an aldehyde functional group, the common way to draw it involves showing the hydrogen. It wouldn't be wrong though to draw it just like that. It wouldn't leave off the hydrogen. In fact, if you draw an aldehyde on mold view, that's what it'll show you when you clean it up. But just make sure that doesn't throw off your count when it comes to your number of carbons. So hexanone, and with hexanone, we do need to specify where it is, because you could have 2-hexanone or 3-hexanone. So it's 2-hexanone with 3 methyl groups. So 3, 4, 5. And when it comes to deciding which side is carbon 1 in this case, again, we have to specify where the carbonyl group is, but it's always, we want to keep that number as low as possible. That matters more than anything else that we name with the prefix. So 3, 4, 5 trimethyl 2-hexanone, and then this just has some stereochemistry. So let's make sure that the answer that I wrote up there before is right. Got for carbon 3, we've got priority 1, priority 2, priority 3. In the hydrogen sticking out. So that's priority 4. We can either rotate something around, or we can step through the board and look the other way. I think we're all comfortable enough doing that at this point. If we don't need to do that, we can just say, okay, that's counterclockwise, but if we're looking from the other side, it'd be clockwise, which makes it R. Just been a minute since we did one of those. Do the same thing over here. We get 1, 2, 3 clockwise, but if we stepped through, it'd be counterclockwise. So 4S. Anything particularly tricky about this one?
Just proper
It does get a little bit weird because that's carbon 1. You have to be careful with it. So it's going to be 2,2,5,5 cyclopentanone. And just like with alcohols, we don't need to specify where the ketone is because it's on a ring structure. It's carbon 1. The only real trick with D, this is one of those examples where it's not just your longest continuous carbon chain. It's your longest continuous carbon chain that starts here. So it's symmetrical, so it doesn't matter which way we count. We get 1, 2, 3, 4, 5, so it's gonna be pentanal. 2 propyl pentanal. And then the last wrinkle is when we have one of these weird aldehydes attached to a cyclo group. We just use that carbonyl term. So this would be cyclobutyl or cyclobutane carbaldehyde. For some reason, the term carbaldehyde always makes me think carburetor, but they don't share a root in common unless you consider carbon as a common root. But I don't think that's actually where carburetor gets its. It might be because it's adding carbon and oxygen in the right ratios. Its whole job, right? Before it gets to the engine, so it might be carbureting something. Might be mixing carbon and oxygen, air. Might be where it comes from now that I think about it. I mean, that's why I really thought about it, even though like when I write it out, I always think carburetor.
Yeah, I thought carburetor too, when I wrote it down.
All right, let's do some quick ones the other way. Yeah, I'll give you a heads up. All right, let's start. Start with parent molecule. 4 ethyl. 1, 2, 3, 4. That's going to be where our stereo center is, so I'm not going to fill in. I guess we do this. We want it to be S, so we want our priority to go counterclockwise, and the side with the bromines is going to be the higher priority, right? So if we put the bromines over here, then we're going to have priority 1, priority 2, priority 3. So that's the wrong direction. Again, when I have to draw a specific stereoisomer, if it's not a molecule that I have the stereochemistry memorized, that's always my approach. You get a 50-50 shot getting it right the first time. So draw something. If you get it wrong, just switch it. And actually, you can either switch where you put the bromines, or you could switch the wedge to the dashes. Would have the same result, right? Switch one of the 2 things. Or switch 2 over the 4 substituents. And then get the other stereoisomer. There's a 3-pentanone, 2,4-dimethyl. Nice and symmetrical. All that symmetry means no stereochemistry to worry about. Took our butanol. There's 3 bromobutanol, and then see if we get the right. Very nice. First priority is bromine. And then the aldehyde side. So we did get it. Just important to remember. Even though the aldehyde has highest priority when it comes to numbering. When it comes to assigning priority for stereochemistry, we go back to the atomic or to the atomic numbers. Easy enough, right? I always find going from the name to the structure. Name to the structure I've always found personally seems easier, makes more sense because you can draw it however you want as opposed to being locked into whatever structure you're given by the test. All right, so let's talk about some reactions. We have had some reactions for producing aldehydes already. Because we did have oxidation of primary alcohols to make an aldehyde. If we were careful, we couldn't use chromic acid, we couldn't use a strong oxidizing agent. Because then we would oxidize all the way to carboxylic acid. But we had several options. PCC was our chromium-based option, so good yields but highly toxic. DMP or DMSO both work as well. We have a couple options, but the key is that we're starting from a primary alcohol and using a weak oxidizing agent or mild oxidizing agent. Ozonolysis will also give us an aldehyde if it's the right alkene. So ozonolysis is a little tricky to use as a synthesis tool. But in the right circumstances, it can be pretty helpful. Then this one's a bit of a throwback, beginning of last quarter. Hydroboration of alkynes. Alkenes give us an alcohol when we do the hydration reaction, right? But if we do hydration reaction of an alkyne, we get a carbonyl. Because first you make the enol and then it rearranges to make the carbonyl. So if we do the anti-Markovnikov hydration of an alkyne, we can get an aldehyde. So all 3 of these, this is why class 2 carbonyls tend to get lumped together, because we can make ketones using all 3 of these methods too, right? We just have to have different starting material. Or in the case of the alkyne, we use the Markovnikov version instead of the anti-Markovnikov. Right, so it wouldn't we wouldn't want oxidation of a primary alcohol to make a ketone. If we were trying to make a ketone, what would we oxidize?
Secondary.
Yeah. Tertiary is never an option, right? Because you already have 3 bonds, 3 carbon-carbon bonds. So oxidation of primary gives you the aldehyde, and you have to be careful not to over-oxidize it. We don't even have to worry about that. Making ketones is even easier because we don't have the furthest we can oxidize, short of burning it, taking it all the way to CO2, is making the ketone. So we can use the stronger oxidizing agents, chromic acid or dichromate or whatever's around. These would still work though. Although, I think I have a slide on this a little bit later, aldehydes are more reactive than ketones. Because you get a stronger difference in charge on the carbonyl when it's an aldehyde compared to a ketone. And so you might not get quite as good of a yield if you use the mild oxidizing agents on a ketone. They would still work in theory, but you'd probably be better off using the stronger oxidizing agents since you don't have to worry about over oxidizing. If we're gonna make a ketone from ozonolysis, what would we have to change? It's basically, we just need a tri-substituted or a tetra-substituted alkene, or an alkene that has two R groups on the same side. I guess is the more universal way of saying it, because you could, in theory, put a hydrogen there and an R group there. And that's going to get turned entirely to CO2, and then you get your ketone. You'd only chop off a single carbon in that case. So there's a couple options there. And if it's not hydrochloration, if we want the Markovnikov oxidation of an alkyne, or sorry, Markovnikov hydration of an alkyne, that's one that was sort of the combination of our other two hydrations. The acid catalyzed mercury, acid catalyzed oxymercuration mechanism gives us the Markovnikov addition, which then turns itself into a ketone on the second carbon of the chain. And so next slide is just what we just talked about. Oxidation of secondary alcohols, ozonolysis of the right alkene, acid catalyzed hydration, so H2SO4, H2O with mercury sulfate. And then we also did just add one last chapter, that Friedel-Crafts acylation did give us a ketone as well. All right, so let's do some practice from a synthesis point of view. Try it without consulting your notes too much. See if you can fill in the right reactants. At least name the reaction, write the name of the reaction, even if you have to go back and remind yourself what are the specific reagents for that one. So the review slide here. For oxidation of secondary alcohol, say dichromate under acidic conditions, sometimes. You could also just add chromic acid, because that's really what you're making here. We put sulfuric acid with dichromate, make chromic acid, which is actually the reactive part. So writing it either way would work there. Or I guess you could write dichromic acid, H2Cr2O7.
Yeah, that's what I would.
That works too. If you actually assign oxidation states for chromate versus dichromate, the chromium is the same oxidation state in both cases. So they're really similar reactivities. Just under the right conditions, you basically dehydrate a chromium. You lose one oxygen to link two chromates together to make dichromate. But the chromium is the same oxidation state, so it doesn't matter too much which of those options you use. PCC or the DMP does right the name, yeah. Terminal alkyne. Oh yeah, we want the Markov link one, so the acid catalyzed. So H2SO4, Hg. I think it actually has water listed as well, and then mercury sulfate, mercury 2 sulfate. If we want the anti-Markov, we do the hydroboration. So the BH3.
I always use BH3. Which I know they list it as like, sometimes they list it as like
Yeah.
R2BH.
So it changes the stoichiometry a little bit. I think with the alkynes in particular, you don't want to use BH3 because you can wind up with it reacting twice. If you only want it to react once to stop at the carbonyl, then you want to use that HBr2.
Yeah.
And then second step was H2O2 and AOH. And that does simplify the stoichiometry because then it's 1-to-1 instead of 3-to-1 as well. Not like that's a tricky math step, but. And plus, if I'm remembering correctly, I believe that these alkyl boranes, dialkyl boranes, are solids and have a longer shelf life than if you just borane, which might even be a gas at room temperature. So practical concerns. This is an ozonolysis one, right? It's an ozonolysis that's going to give us now and a ketone. Very good. So step 1, ozone. Step 2, mild reducing agent, usually BMS. You do this a couple different ways. There's a one-step approach. If you start from the right acyl chloride, right? We're going to do a Friedel-Crafts acylation. So if we just start with that acid chloride. Plus aluminum trichloride. Get that. Alright, so I'll review, but just sort of in new context. And now we have the nomenclature names too, like yes. This one's probably the only tricky one to name. Looking at these. Rest of these. We probably, the easiest way to name this is use the old school naming system. Hey, Steve.
Hi.
How can I help you?
Do you have an actual class?
Yeah. This is our normal class. Who are you looking for?
I'm meeting with Keely and the rest of them. T104.
T104 is that way. This is S104.
Sorry about that.
No worries.
Give you the charades.
Really the easiest way to name this would be that old school naming system, because you could call it phenyl isopropyl ketone and be done with it.
Oh, that is true. Yeah.
Because otherwise you wind up with a ketone on carb. I guess you could say that it's you wind up with a ketone on the end of your longest continuous carbon chain, which in theory can happen.
Can't do that, yeah.
So actually, I would look that one up on MolView, frankly. Let's see, you can build it real quick. While you guys do that, I'm gonna pull up our the textbook. Because we also have a bit of a conundrum here. If you have a ketone and an aldehyde on the same molecule, which one takes precedence and what do you do with the other one?
Okay, so the common name isobutrophenone.
Isobutyrylphenone. Okay,
And then the systematic name's 2-methyl-1-phenylpropane-1-O.
so they do name it as
So they do name
as
it.
propane, as propanone, but it's one propanone, which normally can't exist.
That's weird.
It is. And then I'll also point out. So Klein in particular is the one that I always default to. But most OChem textbooks will actually have an appendix at the back. That is the nomenclature, IUPAC nomenclature as an appendix. And you somewhere in here is going to be a list of priorities. There we go. So highest priorities. What's that?
That says the top, the highest.
Yeah. So carboxylic acids will always be named as carboxylic acids. And if you do need to name it as a substituent, like say you have a molecule that has a common name and you added a carboxylic acid group to it, you add carboxy as a prefix. So you can have carboxy testosterone. You're not gonna go back and do a systematic name for testosterone.
That would be kind of torturous.
That would be torturous. But so what you'll do instead is you add carboxy as a substituent. So if we're looking down the list here, aldehydes have priority over ketones and they both have the same substituent name. So we would name it as an aldehyde and then add an oxo
If there's two of them.
if there's another carbonyl on there. So to go back to, yeah,
But that also just do put it in.
no, I think it's probably because, like I said, there's a slide on this, one or two slides down the road. Aldehydes are more reactive than ketones,
Okay.
so they're gonna get priority. So that would be 1, 2, 3, 4, 5, 6. So it's gonna be hexanal. The 5 oxo. Hexanal. But again, if it's a molecule that shows up in biology, in, you know, yeast or something, it's almost certainly gonna have a common name. Like pyruvate is not an IUPAC name, but it's one of the most common molecules that we see. All right, so when in doubt, go find that appendix. Or some other version if you, I'm sure if you use the search engine to find like organic substituent priority functional group, you're gonna get up, you know, that table showing up all over the place or something similar. I just found out from, it's interesting raising kids because you see how language changes. Googling something is not what they say anymore. In elementary schools and middle schools, they say search it up. Because nobody wants to use Google anymore, because Google's garbage now. Even if they're using Google, they don't say Google it, they say search it up.
I remember it was, you Google it.
Right.
You Google something.
I don't care what search engine you use, you Google it.
You Google it, yeah.
It's like Band-Aid or Kleenex, yeah.
Google is quite attractive.
Yeah. Their results are pretty garbage. Better than Yahoo. I use DuckDuckGo. They don't track your searches as much.
Yeah.
They're a little bit more privacy friendly and they're a smaller company. Their results aren't as good. Occasionally, if I can't find what I'm looking for in the first 2 pages, I have to try Google and see if it got any better.
I use Opera GX because it has a very good RAM limiter in it.
Oh, interesting. Okay.
RAM in your computer.
Yeah.
So you can actually have like a decent amount of tabs open. I hate closing tabs.
If I did that, I would never close any tabs and then I would, yeah. All right, so we can take a break now. We have 2 mechanisms for the addition here. So we could power through and be done in about 20 minutes. Or we could, you're writing them down already. Anyway, what do you think, Jerry? Go power through or take a break?
Power through.
Power through. Let's do it.
The energy. Yeah, so.
All right, so when we have a class 2 carbonyl and we have a nucleophile, if it was a class 1 carbonyl, we do a substitution reaction. Class 2 carbonyl doesn't have a good leaving group, so what we wind up with is your nucleophile is attracted to where there's the most positive charge on the molecule, which is the carbonyl carbon. Makes a lot of sense, right? But in order for your nucleophile to attack, you've got to break that pi bond. So really straightforward mechanism. Nucleophile attacks and the pi bond breaks at the same time. And then you just have a deprotonated alcohol. So your next step is just a proton transfer. You might note also that the figure of the acetone here has shows a triple bond. That's just because the software that computational chemists use to make these figures, by default, it'll display the number of bonds based on the distance between the atoms. So acetone actually has a slightly shorter carbonyl bond than most carbonyl bonds.
So it thinks it's triple.
So it shows up as the triple bonds.
Oh, that's interesting.
Because again, it's the same software that you'll use when we do our computational labs.
Mm-hmm.
It basically just takes in these atoms in Cartesian coordinates, and then the bonds are not coded into the Cartesian coordinates, just the nuclei. And so then it fills in the gaps here. So if you actually went into this software and just grabbed one of these hydrogens and pulled it away, eventually that bond just disappears. Once you get it far enough away. And if I took it, why is hydrogen not a good example? But I dragged this carbon closer to that carbon, it would show up as a double bond and then a triple bond as they got closer. So I just didn't catch that when I made this figure. Yeah, it's an interesting side note. So in general, like I mentioned before, aldehydes are more reactive than ketones. And that's because we only have one electron donating group. electron donating groups are gonna stabilize ketone, or it's gonna stabilize carbonyls. Because that partial positive gets extra electron density from the R groups that are attached, and that makes it less positive. Makes a lot of sense, right? When we've been talking a lot about electron donating with it versus withdrawing. 2 electron donating groups is gonna make that a less attractive target for a nucleophile. So an aldehyde is gonna be more reactive, and formaldehyde, methanol, is gonna be really reactive because it has no electron donating groups attached to it. That's why it's sort of its own class. As it comes to reactivity, and in fact, this same reaction, if you actually, formaldehyde solution that they use for preservation is actually formaldehyde mixed with water. And you actually don't get formaldehyde as formaldehyde in that case, because it's so reactive that you wind up with, if you have the aldehyde and a water molecule, you actually wind up with this reaction happening. Where you just wind up with the water acting as nucleophiles. So you actually wind up with methane diol. It's the dominant, is the most common compound in that formalin solution. Which works because it's also a really good preservative. It kills things. So it's not actually that bad to have around. But that's why it's called, they say formaldehyde, or the smell is formaldehyde, but what's actually present in the solution is that methane diol.
But aldehydes have less electron donating thing, but more reactive.
Correct. So that also means that if your R groups are electron withdrawing, you can make a ketone a little more reactive. That's what we saw in lab on Tuesday, right? We used benzophenone, which was the ketone where both R groups are a benzene ring. So that creates a lot of resonance, but both of those benzene rings have all those conjugated bonds are gonna also be slightly, well, I guess maybe not. What would the resonance structures look like for benzophenone? So you're gonna wind up pulling electron density towards the oxygen because the only resonance structures are gonna be the ones that look like that, right? So even though we had, that would actually be pretty strongly electron donating. My initial thought was electron withdrawing because we've been talking about aromatics, right? And having all these conjugated rings, but if we actually look at it, in this case, the benzene rings are going to be electron donating to a carbonyl. And it still works. The reaction still works. We didn't wind up overstabilizing it like we did with the cinnamaldehyde. Those Grignard reagents are kind of nasty.
With all the rotation, feeding electron density for the oxygen, would that make it a better group?
So in general, donating electron density doesn't make things better leaving groups. It makes them worse leaving groups. Because more electron density is going to strengthen those bonds. Electron withdrawing groups make bonds weaker because there's less holding things on. And we usually think about that in terms of acidity in proton transfer, more so than other leaving groups, but it does apply to other leaving groups as well. No, I guess not. In SN1 reactions, this is what you get when I'm sleep deprived. With SN1 reactions, they're more your leaving group can leave more readily because you have more electron donating groups stabilizing the carbocation that's left behind. All right. Did we need to do this? So I guess the next slide is just. What nucleophiles can we use? Well, how much time we got? Anything that can act as a nucleophile can act on a carbonyl. Some, the weaker nucleophiles are gonna work better on the aldehydes, but they'll all work relatively well. And so a big chunk at this stage of the course is being able to recognize, is my reactant an electrophile or a nucleophile, right? Like we saw that with the aromatic rings. So as soon as you see a carbonyl and a nucleophile, start thinking addition reaction. Because nothing about this necessarily is specific to basic conditions, right? What about this is going to be most specific to basic conditions? I mean, nucleophiles generally work better under basic conditions.
Yeah. I was just saying, probably just like the proton transfer part.
The proton transfer part. Like basically, if they are under acidic conditions, it's going to be kind of hard to make this.
Right. Just because there's no need for that proton to actually move around.
So if we have a neutral nucleophile, a weaker nucleophile, and we're under acidic conditions, what's going to be the first thing that happens then? If we can't make this intermediate and then proton transfer, what can we do? We have lots of H pluses floating around. What part of this molecule are they going to be attracted to? We just protonate the carbonyl first. And then
So it kind of just reverses.
Exactly.
Okay.
Oh, tertiary carbon, carbon cation.
Let's see. So if we had to ask, let's just use ammonia. Let's just use water. So if we're under acidic conditions, first things first. We protonate. We get an oxygen with 3 bonds, so positive charge. And then a weak nucleophile can come in here. And then we actually will wind up with one more proton transfer step at the end. Just because we don't usually stop when we still have a positive charge. But really the bulk of the reaction is done once we get here.
Another proton transfer.
And then another proton transfer, so we wind up with, if we use water as our nucleophile, we get a diol, which is exactly what we just talked about, right? With formalin. So the only difference in acidic conditions versus basic conditions is, does your proton transfer step happen first or second?
It's basically.
Yeah. Like I said, the biggest trick with this is that your nucleophile is not necessarily going to be a strong nucleophile, because your nucleophile is going to be in its protonated state in all likelihood. Unless your nucleophile is something like chloride. Alright, so last slide for today. I am drawing out the base version from on a fresh sheet of paper. Try drawing out the base catalyzed and the acid catalyzed mechanisms. Point of a Grignard reagent that makes a carbonyl nucleophile, right? So basic condition, because Grignard reagents have to be under basic conditions. Nucleophile attacks. Against our final product. So we went from cyclohexanone to 1-ethyl cyclohexanol. Right, so and then in this case, we've got the HCl. First step is you protonate your oxygen. And this is where just trying to follow the charges can lead you astray if you're not careful. Because it's tempting to say that, well, if you've got a nucleophile with a negative charge.
That's what I did.
That's exactly what I was trying to go for.
But that's gonna push you have to remember that pushes your extra electrons over here, it's gonna just make a carbanion here. We know those aren't very stable.
CO for the tertiary.
So the Cl is gonna go secondary carbon. The oxygen doesn't count, so it doesn't matter. And that gives oxygen its electrons back. Because the other thing to remember is we're never gonna make two electronegative elements fight over electrons just to leave a negative charge right next to it on a carbon. It would be kind of chaotic. So hopefully when you drew that step, You immediately recognize,
No, I
oh, wait,
recognize that.
that looks weird.
I didn't even try, I was just like, no.
Exactly. So, and that's where we've now been doing this enough that you're starting to get some of that chemical intuition where you can kind of feel your way through a mechanism a little bit. You don't want to rely on that on the test, obviously. It's way too easy to, you know, freak out or under time pressure, just draw things that don't make sense. But you should be able to start trusting your intuition a little bit because we've been doing this long enough and it's always the same rules, right? All organic chemistry is electronegativity and where do the electrons go?
Just following the electric.
All its electrons. So then after we do this step, we'll wind up with our final product. So in this case, because our nucleophile did have the negative charge, we don't need a follow-up proton transfer. All right, and so that's the simplest. That's the bulk of the reactions that we see with carbonyls and aldehydes are those two mechanisms. The trick is that these mechanisms are reversible. Well, if your nucleophile is a good leading group, obviously we're not going to. This one's not reversible because we're not going to have ethane leave or the ethyl carbanion leave as a leaving group, but this one's reversible. And this reaction is why we get the two different forms of carbohydrates. You have the open chain form and the ring form of like glucose, for instance. It's because glucose exists as a carbonyl, but it's also attached, has a bunch of alcohols that can act as a nucleophile on the same molecule. So if you have something like, I think glucose is an aldose. I'm going to get the stereochemistry all wrong, but that's not the point. 1, 2, 3, 4. Then a CH2OH. It's only 5 carbons, so there's one more before you get to the CO2OH. Basically, what happens is you wind up with this oxygen doing the same reaction.
Just from one end of the molecule to the next.
So you wind up making a ring structure that's a cyclic ether, but it goes back and forth because that's a good leaving group.
Is that considered a rearrangement or is that?
We call it an isomerization. It's not just a rearrangement, because there's more going on than just a rearrangement, but yeah. So we're going to talk about these and we'll get a little bit into carbonyl or carbohydrate chemistry as part of it. So fun stuff. We'll go ahead and end there. There'll be a quiz this weekend. It'll be something similar. Draw a mechanism, draw some products.